Good afternoon, everyone. Let's continue our exploration of filament winding challenges. Today, we're focusing on winding shells with convex-concave generatrices in WinderCam software.
Exactly. We'll walk through the nuances of preparing winding programs for these complex shells. Our example is a hypothetical structure built from two liquid rocket engine nozzle profiles, combined into a single contour for one winding cycle.
First, we extract a unified external profile, stripping away internal technical details so we deal only with the generatrix. Then, we attempt to wind a heat-resistant tape over it. Keep in mind 2 points. The dimensions along the generatrix are conditional and relative, and the X and R axes on the profile graph use different scales.
From the very beginning, equipment choice becomes critical. A 3-axis machine with a self-aligning head is unsuitable here. After concave sections, the subsequent convex areas would clearly interfere with the counterweight of the laying head. So we choose a 4-axis filament winding machine as the most appropriate option for our study.
Our first attempt is straightforward. We try to solve the problem head-on, using the raw parameters from the given profile. We have a defined shape of 2 connected tanks wound in a single cycle. Important parameters: mandrel length of about 484 millimeters, maximum radius around 69 millimeters, minimum radius in the neck at about 29 millimeters, and a tape width of 10 millimeters.
For this first trial, we pick a pole hole diameter of 10 millimeters. Since we have no strict selection criteria yet, we set the safety distance to 20 millimeters by default. With these parameters, we run the calculation and obtain a very nice initial winding path.
The result looks promising. To ensure a solid shell without gaps, we adjust this initial ply slightly, making a minimal change to the winding pitch so that the coverage becomes continuous. Up to this point, everything is going smoothly. So far, the flight is normal.
Next, we mentally place the mandrel onto the selected 4-axis machine and begin computing the movements of the actuating links in the motion system. The starting position, at first glance, appears quite decent. No obvious problems are visible.
Then we start the motion and, oops, we see something that may not be unimaginable, but is certainly impossible to implement in real mechanical engineering practice.
Fortunately, we still avoid collisions between the mandrel and the machine mechanism. The predefined safety distance protects us there. However, the free span of tape stubbornly tries to move inside the surface of the mandrel. In reality, the tape would slide with varying degrees of success along the surface and over the already wound plies, scraping fibers and causing damage.
The support carriage dashes frantically back and forth, desperately trying to lay the tape, even if that means doing it from inside the mandrel. One thing is obvious: with this particular parameter combination, the winding program is not implementable.
The question arises, can this situation be corrected? Under what parameter values would it become feasible? The first idea that comes to mind is to vary the safety distance, but I can assure you, even without showing the illustration, this does not lead to any improvement, even when we reduce the safety distance down to 1 millimeter.
So what else do we have at our disposal? Of course, we still have the pole hole radius as a parameter, and here we finally get our first truly rational idea. In our failed initial calculation, the main problem is to lay the tape into the concavity.
In that region, the tape orientation angle is so small that the payout point is located too far from the contact point. The free span of tape becomes too long. However, the robust Clairaut equation for the geodesic line gives us a fortunate opportunity to adjust the change in winding angle over the entire mandrel surface, and therefore in the critical zone.
So let's get to work. We increase the pole hole radius. This will increase the ratio R0 to R max, and thus the winding angle alpha, where alpha equals arcsine of R0 over R, and R0 is the pole radius corresponding to the midline of the tape.
For the problematic zone, this means that the tape will be laid more easily into the concave region of the mandrel surface. Let's test this. We increase the pole radius to 32 millimeters.
And here we immediately encounter a new issue. We hit the upper limit for the pole hole radius, which is the neck radius. Mathematically, the shell splits into two parts, similar to a hyperboloid reaching certain boundary parameter values.
So we now have a clear upper constraint. R0 must be less than RP, the neck radius. We try R0 equals 24 millimeters. That is still too large. Then we test R0 equals 23.5 millimeters. Good, now we manage to reach the second neck. By trial and error, we determine the boundary value R0 equals 23.39 millimeters.
But something still feels off. The second neck looks more tightly bandaged than it should. Let's check the thickness distribution. Since this is the boundary case of the winding angle, we expect to see something undesirable there.
And indeed, the calculated thickness graph shows an anomalous peak in the right-hand concavity. This confirms our suspicion. It becomes clear that we should avoid the upper limit and instead stay closer to the lower bound of acceptable values.
So we restart with R0 equals 20 millimeters. This time the results are excellent. The thickness distribution is perfectly acceptable and looks well balanced across the entire surface.
Satisfied, summarizing, now that we've debugged what happens on the mandrel, we return to the earlier unresolved issue, the motion of the actuating mechanism itself.
In this part of the simulation, things still don't look great. When the support passes the first concavity, it rapidly moves to the left, and then something unacceptable happens, a reversal of motion. At that moment, the tape payout speed from the roller almost becomes negative. Tension drops to zero, the tape sags, and the process breaks down.
So what control parameters do we have left for this part of the problem? Essentially only one, the safety distance. If we increase it, the amplitude of the reversal will grow. That is clearly undesirable. So we move in the opposite direction and reduce the safety distance, trying a value of 7 millimeters.
The reversal doesn't vanish completely, but it becomes significantly smaller. At a tape width of 10 millimeters, this safety distance is already right at the limit, so this combination of parameters is likely close to optimal for a mandrel with such a complex shape.
So, in the course of calculating this winding program, we have solved 3 key problems. First, we ensured that the mandrel can be fully wound from edge to edge. Second, we achieved an acceptable thickness distribution in the concavities of the mandrel. And third, we minimized the support reversals.
We sincerely wish you success in your own calculations with windercam.de. Experiment, analyze your profiles, and don't hesitate to push the limits of complex shell geometry.
And we are looking forward to receiving your requests for new features in WinderCam. Your practical cases and ideas help us evolve the software and tackle even more intricate winding scenarios.
Friendly closing. Thank you for watching and listening. We hope this detailed case of a convex concave shell gives you useful insights for your own projects. See you in the next presentation.
Polite, final. Until next time, good luck with your winding simulations and real-world implementations.